Okay, chapter 2 in the second section we're going to break into two parts. So today we're just going to talk about, so in this section, in this video we're only going to be talking about what is a density curve, and also how to find the mean and the median on a skewed one as well as the normal one. And then we're going to understand the concept of the normal distribution and estimate some areas based on the properties of normal distribution. So when we are talking about exploring quantitative data, we always are going to start with plotting the data, choosing the correct kind of graph. Dot plot, sometimes stem plot makes the most sense, sometimes histogram, sometimes box plot. Then we're going to look for the overall pattern, center, spread, and shape, and comment on the outliers if they affect things. Calculate numerical summaries that allow us to figure out the center and the spread, so 5-number summaries or such, or the standard deviation, etc. And then this new piece that we're adding is the idea that if the observations are so regular, they're very close to us, you can see a smooth curve that'll go around it. We're going to start looking at those smooth curves, which are called density curves. Now this particular histogram shows vocabulary scores, and then the density curve has been overlaid on it with this red line, and then underneath the red line, that is considered the density curve. And basically the parts that jut up are squeezed underneath, right? So it's a nice smooth curve, and then we model our information based on that. So we're going to go ahead and bring it back down to here. And a density curve, definitionally, will always be on or above the horizontal axis. So you notice that here we are not below that horizontal axis, and the area underneath it is exactly 1. So an area of 1, 100% of the percentiles, as it were, the 100% of the data. So a density curve is an idealized description of the distribution of data. And when we talk about the actual data, so we're talking about the histogram from before, we would talk about the mean being x bar, and the standard deviation being the standard deviation of the population itself. Once we make a model of the data, then we're going to go ahead and use the term mu to stand for the density curve that approximates or idealizes that distribution, and then this is the mean. And then sigma indicates the standard deviation of the density curve. We're going to spend some time working with all these letters in a couple of days so you can keep them straight. When we are looking at a normal curve, symmetrical, unimodal, and we're talking about the measures of center, median and mean will be right together because it's symmetrical. But for a skewed distribution, the median is going to, just as it is with a normal, it's going to indicate half of the area is below and half of the area is above, right? Half of the area is above. But the mean, because it's skewed, is going to be like a balancing point. So if I had to make sure that it didn't teeter-totter, that mean's going to be the balancing point, and it'll of course be slightly to the right because the outliers are pulling that data to the right. You can go ahead and read this information and then decide what you want to write down, whether it's a sketch or just the words in your notes to clarify for yourself. So the minute that we decide that a set of data is symmetrical and single-peaked or unimodal and bell-shaped, then we can start to use the properties of the normal curve to make predictions and such as that. But the minute that we take the actual data, which we know is all of the set of data, which is x1, and we've found the mean, and we call that x bar of the data, and then the standard deviation of the actual data. The minute we decide to use the model of the normal curve instead of the actual data, then we're gonna talk about mu and this, which is mu, which stands for the mean of the normal curve, and theta, which stands for the standard deviation of that normal curve. Once we decide that a set of data is symmetrical and has a single peak and is creates a clear curve, then we can, instead of using the actual data, we can use the model of the normal curve. And the minute that we say that, we're going to say that it's a normal distribution, and we've got to define the particular normal distribution with the mean and the standard deviation, and that will tell you how to label that curve. So if we had Tim Lincecum's, his mu was 8.2 and his theta is 2.8, his standard deviation, then we could take that normal curve and we could go ahead and label it like we've been doing in class. So we'd go 8.2, one standard deviation away would be at 11, etc., etc., etc. So by saying this, or even more abbreviated by using that, we know an entire curve. Normal distributions are seen all over the place, like with our Oreos. Very often with chance outcomes, there's a very clear symmetrical, this is the sum of two dice, and then all the things we say about SATs and any of the things we want to predict about percentiles, or what's the probability that you're going to get around normal distributions. We do a lot of things around that. No, we won't. No. The normal curve has real specific areas. Now remember, the area under the curve, the whole curve, is 100%, or the area is 1, and then we have 100%, always described in decimal form. So we would talk about 95% as being 0.95. So when we know the way that the normalized curve sets out in terms of percentages, then we can also use what we know about the mean being right there at the 50th percentile, right? And we can use all of the other breakdowns as well. So since this is 68% of the data, we're going to be talking about, on this side of the mean, 34% of the data, approximately. And then this is 13.49. And this is 2.49, and this is tiny. So we can use that to estimate what happens. So remember that the percentiles always talk about at the cut point and below. So here, if we're asking for 11.473, here's our cut point and below. So there's more than one way to do this, but I'm just going to take 50% being there plus another 34%. So it would be 84%. You could add up all the little pieces. There's a couple other ways of getting there, but it's basically, you need to recognize, you look at your cut point and add all the stuff behind it. So remember that percentiles and the probabilities and the areas and all that stuff, the numbers, if it's given it to you, you're going to know that it's talking about how far it is, how much area it is, or what's the probability that it's below it. So if we're trying to figure out the percentage or the probability of what's above it, we need to pay attention to that. So in this case, definitely read the question really carefully and realize that we're talking about more than 11.55. So this is going to be the 2.49 and the tiny 0.13. So it's about 2.5%. percent of a chance that the cookie weighs more than 11.5. So that means if there were 100, we would expect maybe 3, maybe 2 to be more than 11.55. For some reason, this did not carry through. So this is the z-score is the piece of data minus the mu, which is the standardized mean, and then divided by the standard deviation. The normal distribution always has a 0 as the mean, and then 1 standard deviation is your 1 theta and 2 theta and 3 theta, and then -1 theta, etc. So we can absolutely take z-scores on non-normal populations. You know, we did that with the home run hitters, and we were able to compare against different eras. But z-scores are used on normal populations a lot to really find the area under the curve, which is also can be described as the probability of falling in a certain place or a percentile, all found from that z-score. And then you are going to learn how to work forwards and backwards algebraically, as well as forwards and backwards using a table and a calculator. So we're just going to do a forwards one where we're going to find the z. We don't know what the z is, but we do know the data point or the cookie, and then we're going to go ahead and subtract the mean from it and divide by the standard deviation. And then when we're done, it's going to tell us how many standard deviations away from the mean an 11.5 gram cookie is. 11.5 minus 11.392 divided by 0.081. Oops. So the z is 1.33, which means that if this is our mean, and here's 1 standard deviation away, and here's 2 standard deviations away, our piece of data is right about there. So it's 1.33 standard deviations away from the mean. So we have just in this slide deck dealt with those pieces of information, and we will deal with the other one in the next video.